Hello everyone, welcome to our channel Mathematics Parshala. This is a problem of CSIR NET December 2023 Mathematical Sciences. This is a problem of linear algebra part B. The question ID is 704031. First we read the question. Let this be a bilinear, symmetric bilinear form on R2 such that there exists non-zero VW belongs to R2 such that this VV greater than 0 greater than WW and VW equal to 0. Let A be the 2 by 2 real symmetric matrix representing this bilinear form with respect to the standard basis. Which one of the following statements is true? So now the question is about bilinear form. Actually, a mapping from this R2 cross R2 to R. When V is a vector space over the field R, then a mapping say F such that this V cross V to R is said to be bilinear if it is linear in both coordinate. So we can denote this by this F by this. So now for this bilinear form, there is a matrix like that linear operator. There is a matrix representing that linear operator. So exactly in similar manner, there is a matrix representing this bilinear form, and that matrix is defined in this way. This when it is from R2 to R2, then this matrix is a 2 by 2 matrix, and the element will be like this. This first element is actually, if we take the standard basis, this matrix will be with respect to standard basis. So we know that the standard basis of R2 is E1 E2. This is a standard basis where this E1 is 1 0 and this E2 is 0 1. So now this will be E1 E1, this will be E1 E2, this will be E2 E1, and this will be E2 E2. So this is the matrix representing this bilinear form with respect to the standard basis beta. So now look at the options. Option 1 is A square equal to 0. Option 2 is rank A equal to 1. Option 3 is rank A equal to 0. And option 4 is there exists some U not equal to 0 belongs to R2 such that this UU equal to 0. So for this, if we take a matrix A1, a 2 by 2 matrix A1, a diagonal matrix 1 0 0 minus 1, consider this matrix and consider the bilinear form xy is defined by this x transpose A1 y. Then clearly this is an easy exercise for you that this will form this will be a bilinear form on R2, and also the matrix representing this bilinear form, that is A, will be equal to our here this E1 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 E1, this is E1 E2, this is E2 E1, this is E2 E2, and clearly we can find this will be actually our A1, because just calculate that what will be our E1 E1. This will be our E1 transpose A1 E1. So this is our 1 0 transpose column vector 1 0, so it will be 1 0, and a1 is our 1 0 0 minus 1, and this is our 1 0, so this will give our 1, and this is 0, this is 1 0, so this will be 1, so this will be 1 here. Then if we calculate u1 e2, it will be u1 transpose a1 e2, then it will be it will be 1 0 1 0 0 minus 1, and e2 is our 0 1, then it will be 1, and this is 0, this is 0 1, so it will be our 1 into 0 plus 0 into 1, that is 0. So here it will be 0. Similarly, this will be symmetric, is 0, and similarly this will be e2 e2 is 1. So sorry, this will be minus 1. Just check e2 e2. This will be e2, that means 0 e2 transpose, that is 0 1. Then the matrix 1 0 0 minus 1, and this is e2, that is 0 1. So it will be first 0, and from this it will be minus 1, this is 0 1, so it is 0 into 0 plus minus 1 into 1, that is minus 1. So clearly this a is actually this a1. So now check for this bilinear form. See, for this bilinear form, our a is our equal to a1, that is equal to 1 0 0 minus 1. Now clearly here date a will be equal to minus 1, which is not equal to 0. So our rank of a is a 2 by 2 matrix of rank, since date a not equal to 0, so rank of a will be equal to 2. So now look at the option. This a square will be actually here, a square will be actually equal to I. So option 1 for this bilinear form. Oh, okay. Look at the question. We have to check that if this option satisfy, that there exists a non-zero VW belongs to R2 such that this condition hold, this and this. So for this just check, if we take V equal to actually our E1 and W equal to our E2, then check here our VV, that is equal to our E1 just we calculated now, it is 1, so greater than 0, and W bilinear, this will be our E2 just now we calculated, this is minus 1 less than 0, and also we have calculated VW, that is our E1 E2, this is equal to 0. So we have some VW not equal to 0 such that VV greater than 0, WW less than 0, and VW equal to 0. So all the conditions given in this question are satisfied. So for this bilinear form, for this A, the matrix representing this bilinear form A, for this A square equal to I, so this option 1 A square equal to 0 is not true in general. Also here rank of A equal to 2, so option 2 rank A equal to 1 is not true in general, and rank A equal to 0, it is also not true in general, because we have a bilinear form such that the given conditions satisfied and these 1 2 3 options are not satisfied. So option 4 is the correct option, and we now prove this option. To prove this result, that there exists some u such that this u equal to 0. Just we define a mapping phi from closed interval 0 1 to r by phi lambda equal to 1 minus lambda w plus 1 minus lambda ww plus lambda vv. Now clearly here phi 0 equal to our ww, that is less than 0, and phi 1 equal to our vv, that is greater than 0. And clearly phi is a mapping defined by this, so clearly phi is continuous. Phi is clearly a continuous map, so phi is a mapping which is continuous on 0 1, and phi 0 into phi 1 less than 0. So by Bolzano's theorem on continuity, there exists some c belongs to this open 0 1, that is actually 0 less than c less than 1, such that our phi c will be equal to 0, that is 1 minus c ww plus c vv equal to 0. That means 1 minus cw plus cv comma 1 minus cw plus cv equal to 0. So just take here u equal to 0, where u is, just take u equal to 1 minus cw plus cv belongs to R2. So now we have some u belongs to R2 such that u equal to 0, and we only need to check that this u not equal to 0. So if possible, suppose u equal to 0, then we have this 1 minus cw plus cv equal to 0. Then here we have w equal to minus cy 1 minus cv. Now we have vv, that is equal to okay, so take v equal to from here, that is minus 1 minus c by cw. So oh, no need, we will just use vw equal to 0. So we have vw equal to 0. So put here w, that is v comma minus cy 1 minus cv equal to 0, and since it is linear in both coordinates, so it will be minus cy 1 minus c vv equal to 0, and since vv greater than 0, so we must have cy 1 minus c equal to 0, that is c equal to 0, which is a contradiction because we have this c in open interval 0 1, that means this here c is 0 less than c less than 1, so it is a contradiction. So this contradiction guarantee us that this u must be non-zero. So this u must be non-zero, and also this u equal to 0. So we have some u not equal to 0 belongs to R2 such that u equal to 0. So that is proved by defining this function phi from 0 1 to R by this. So phi is continuous and phi 0 phi 1 less than 0. So one such C exists such that phi is equal to 0. That means from this we have such u, that is u equal to 0 where u belongs to R2 and u not equal to 0. So this option is true in general. If such bilinear form satisfies this condition, then for this bilinear form such u exists. So option 4 is the correct option and option 1, 2, 3 are not the correct option. This is the solution of this problem.